Now we have a key result which says that any representation can be broken up into two pieces which are smaller representations. So the statement is that every non-zero, so not on the zero vector space, every non-zero representation of the group G is either irreducible or decomposable. Either it has no interesting invariant subspace, or it's equivalent to a direct sum of representations in an interesting way. I should note here, this is really using that the group is finite. It fails for infinite groups. All right, let's prove this. So we start with our representation, which I'll assume is not on the zero vector space. So I want to show it's either irreducible or decomposable. Let's suppose it's not irreducible. So that means there exists an invariant subspace which is furthermore not one of the dumb possibilities. It's not the zero subspace or the whole thing. What we'll do is we'll show that this invariant subspace is part of a direct sum decomposition. It's one half of a direct sum decomposition. We have to produce the other half. First, we notice the following. There exists a linear map, which I'll call T, from V to itself, such that T of V, the image of T, is contained in the subspace W, but also the restriction of T to W is the identity on W. In other words, T is a projection operator which projects onto the subspace W. Incidentally, these two identities imply that T composed with T is just T again. So this is just linear algebra. For any subspace, you can construct such an operator. In fact, you can construct many such usually. The idea is you pick a basis of W, then you extend it to a basis of V. And then you can define T by saying what it does to that basis. For the first few elements of the basis, which are in W, you'll send them to themselves, and for the remainder, you'll send them to 0. It's a very standard construction. So then what we'll do, taking this linear operator, we'll average it over the representation using the averaging trick. So I'm going to define a new operator, T prime, by the formula that the averaging trick gives, sum divided by the order of G of phi G T phi G inverse. So this is a linear operator from V to V. But in fact, because it's the averaging trick, T prime is not merely a linear operator, it's a morphism of the representation phi to itself. Okay, now I claim that T prime has properties similar to T. For instance, the image of T prime will be contained in W, and the restriction of T prime to W is the identity on W. So therefore, of course, the image of T prime is equal to W. So T prime is also a projection operator. This, by the way, will imply T prime is T prime. So this is all pretty straightforward. We just use the formula for T prime. I'll just write it out again. For claim 1, we have an arbitrary vector V, but we know, we apply phi G inverse to it, then we apply T. One of the properties of T is that this is always in W. Oh, but the representation has the property that W is an invariant subspace, so this also always has to be in W. So the whole thing has got to be in W. That's the proof of 1. How about 2? Well, let's suppose V is actually in the subspace. In the case when V is in the subspace W, this thing will also be in W as well. So this is in W if V is in W. Oh, but T has the property that it's the identity map on the subspace W. So if the original vector is in W, I can simplify this a bit. I have 5G of phi G inverse of V. The T didn't do anything. Oh, but that is just the identity map, so I'm actually looking at a sum of a bunch of copies of V. And now you see why we're doing averaging. The number of copies is exactly the order of the group, so this actually simplifies just to V. I've just shown that if V is in W, then T prime of V is V. That's the second claim. So we've got a new projection operator, but now it's a morphism. So now we define a subspace W prime to be the kernel of T prime, the set of vectors such that T prime of X is 0. Because T prime is a morphism, W prime is an invariant subspace. That was the purpose of having T prime. I claim furthermore that the vector space V is a direct sum of these two subspaces, the original one W and this new one W prime. And if I can show that, then that means that since they're both invariant subspaces, the representation is a direct sum of the two sub-representations, neither of which is 0 or the whole space, because W isn't. And so that gives the whole ballgame. That is a decomposition. All right, let's see why this is true. If I take any vector, x, then I have the following formula. X is T prime x plus x minus T prime x. That's just a tautology. That first term is in W. That's claim 1. The second term is in W prime. It's in the kernel of T prime because of this. So this shows every vector in V is a sum of something in W and a something in W prime. So those subspaces span the whole space. And then finally, if I have a vector in the intersection, well, if I compute T prime of that vector, on the one hand, because it's in W, T prime's the identity on W, so that's X. On the other hand, it's in W prime, that's the kernel of T prime, so T prime of X is 0. So that subspace only has 0 in it. That's the proof that I got a direct sum decomposition, and therefore it's a direct sum of representations. The key trick was taking the projection operator, which wasn't a morphism, and averaging it to become a projection operator.